get the fuck away. What was it? You just told me that your buddy was like riding the bus, and the guy was like, "Do you have any cash that you can spare?" And your friend. Yeah, it's really good to ask them about trauma that could happen.
Okay. Good morning, everyone. Can you confirm if you can hear me clearly? Is everyone hear me clearly? Even those of you online, can you hear me? Can somebody talk online if you are hearing me? Okay, thank you so much. Okay, so I want to welcome you to another statistical machine learning class. Of course, we are counting down to the final exam. I've started grading midterm 2, and of course, you're actually going to see your grade before the end of this week. Now, I will advise that whatever we're going to be doing now, please take it seriously, okay? We are counting down to the final, and final has a very huge weight. Okay, so I want to start, this week with a topic on Graphical-LASSO. Before now, I walk you through what I call graphical models. We actually I walk you through the principle of Bayesian network and so on like that. But you know what? That idea is also going to be very essential in this particular topic. So this particular topic, you can see Graphical-LASSO. We are actually adding something to graphical structure that we've done before. And I'm going to tell you the essence of adding lasso. Okay? So once again, welcome to Graphical-LASSO. In the outline, we're going to have a brief introduction to Gaussian graphical model. Okay? Then what are the challenges in high-dimensional regime? Because the idea behind Graphical-LASSO is to be able to address whatever challenge that we experience in high-dimensional regime. And of course, lastly, I'm going to walk you through how we can actually use a Gaussian graphical model with lasso. Please pay attention. I need you to pay attention. The countdown to final, like I said, starts now. Okay, now I want us to see what I'm showcasing now, because the reason why we call this a Gaussian graphical lasso is because we believe we're working with random variables. We know the random variables that are connected by graph, and of course, they are not categorical. The one we did before, they were categorical. They have levels, but this one is continuous. We are working with continuous random variable that are actually connected by graph, and there's a relationship between them. Now, because they are continuous random variable, we want to impose a probability distribution on them. We want them to be Gaussian. We can also have situations where they are not Gaussian, but the one I want to walk us through in this class is the one where the underlying probability distribution is actually Gaussian, okay? And that is the reason why, because if I have so many variables, and of course, if they follow normal distribution, okay, within statistical framework, we're actually going to use the idea of multivariate normal density, because I got so many variables. So what I'm actually showcasing now, please pay attention. What I'm showcasing now is the density function. They say density function of a multivariate normal distribution. I'll give you 1 second. I think I'm gonna make use of this guy here. Okay, so what I'm talking about, this guy, that's a multivariate normal density. Please pay attention. This is a multivariate normal density. Okay, this is a density function, okay, for so many continuous random variable that we believe that are connected. Okay, now when you take a look at what I just circled right now, we actually there's a particular information that we need in this multivariate density, and that very information is this. Please pay attention. I'm going to explain the difference between the two. I need you to pay attention. Okay? What do I actually need in a graphical lasso? I need a precision matrix. Precision matrix is an inverse of a covariance matrix. I'm going to say that again. Precision matrix. This is what this guy here is a covariance matrix. This guy here is a precision matrix. Now, as you can see, this precision matrix is part of the multivariate normal density. Take a look at that. It's part of the multivariate normal density. Now, what is the difference between covariance matrix and a precision matrix? Why is it that we cannot get satisfied with just covariance matrix? Please, I need you to pay attention. Why is it that with covariance matrix, okay, why do we need a further analysis? Why do we need a precision matrix? The covariance matrix will only answer a questions of how variables relate together. Covariance matrix cannot tell us whether they have a direct, whether the relationship is direct or not. The covariance matrix will miss both direct and indirect relationship. I'm going to say that again. The covariance matrix will miss both indirect and direct. Okay? Precision matrix will only indicate direct. Okay? The precision matrix will remove indirect. Because if you don't remove indirect from the indirect relationship from the graphical structure, your graphical structure will be noisy. Please pay attention. I'm going to say that again. We don't just do what we do. We have reason why we do what we do. Why is it that if you look at principal component analysis, if you look at factor analysis, the focus has been on covariance matrix. Okay, the covariance matrix is only going to answer a question about how variables relate. Covariance matrix will mix both direct and indirect. When I say mix, it's going to give us a mixture of both direct and indirect relationship. But you know what? We don't want indirect relationship. We only want direct. If we want direct relationship, okay, then we need a precision matrix. So precision matrix is actually inverse of a covariance matrix. And if I want to get a precision matrix, please pay attention. If I want to get a precision matrix, I actually want to get this precision matrix from my data. Then if I want to get it from data, then I need to be able to, I can use the method of maximum likelihood to estimate that. And if I want to use the method of maximum likelihood in estimating my precision, the assumption is that I should have an underlying probability distribution. The underlying probability distribution for that now is multivariate normal. And that's why you see here, the multivariate normal has the precision matrix that I'm actually looking for. Is there any question before I move forward? Is there any question before I move forward? Okay, now let me tell you this. If I'm talking about, in a stock market, stock are related, okay? Covariance matrix is only going to give me the idea that stocks are related. But covariance matrix is actually mixing both direct and indirect relationship, But if I want some stocks that are directly connected to some, then I would need precision matrix. I would need to go beyond a covariance matrix. Now, if you take a look at what I have now. Now, if you take a look at this, when you try to plug in, let's say we want to use that notation to represent precision matrix. Wherever we see that in the multivariate architecture, I'm actually going to plug in that notation. When I plug in that notation, my multivariate normal become this. Please pay attention. My multivariate normal become that. You can now see I now have my multivariate normal in terms of precision matrix. So what I have right now is this guy. This is what I'm actually going to be working on. But if you want to know how we derive this, please pay attention. I can ask you in the exam. If you want to know how I derive this, I'm actually going to stop this right now. I attach another material. Please pay attention. Oh, 1 second. I attach another material, okay, on canvas. Please pay attention. I'm quickly going to show you how, because I can ask you to derive that. I can actually ask you to derive that. Okay. Like I said, pay attention. Oh, 1 second. Okay. Now, I attach this material. Let me stop this. I think I'm actually going to. Okay, so I attach this material. Okay, check. I want to show you right now how. Please pay attention. You know, I've been repeating pay attention for so many. I know why I've been saying this. This is critical. Okay? We count it down to the final. Now, if I have x1, x2 up to xn, random variable, they are continuous. They follow normal multivariate, normal distribution. Okay? With zero mean and a covariance matrix. Like I said, this guy is a covariance matrix. The inverse of a covariance matrix is a precision matrix. Okay? Now, let me tell you this. If x1 and x3, okay, are related, let's say for instance, if I have a chain, let me say if I have a chain, if x1, okay, causes x2, okay, and x2 causes s3. Please pay attention. If x1 causes s2 and s2 causes s3, okay? Now, you know what covariance? If you get a covariance matrix for this, you will have non-zeros. It's going to tell you covariance exists between x1 and s3, okay? But precision matrix actually going to say x1 and x3 are independent, given that I have observed s2. Please pay attention. Now, you know what precision matrix is going to tell me? Precision matrix is going to say x1, okay, s1 and x3 are independent, given that I have observed s2. In that situation, where that happens, there's not going to be an arrow again between S1 and S3. Precision matrix is going to be 0. Please pay attention. When S1 causes S2 and S2 causes S3, if you get a covariance matrix for this, your covariance matrix will be 3 by 3, right? Or the covariance matrix will show relationship for all these variables between S1 and S2, S1 and S3. But precision matrix will tell you that even though it look as if there's a relationship between S1 and S3, that relationship is spurious. That relationship is indirect, as you can see. Do we have a direct relationship between S1 and S3 based on this structure? No. The relationship they have is indirect. Precision will remove that relationship. So that is what we mean. And that's why when you remove that relationship, that's why you say theta ij equal to 0, which means when theta ij equal to 0, you know what is going to happen? When I'm going to draw the network, there's the edge, the arrow between x1 and s3 will disappear. And you know what you know the good news? When the arrow disappears, what happened to your structure? Your structure is sparse instead of dense. When your structure is dense, it is noisy. We don't want your structure to contain a spurious relationship. And that is what the precision matrix is going to do, a job of eliminating any spurious relationship, any indirect relationship. And it's actually going to say, okay, these two variables are independent, given that I've observed the rest. That's what it means. Now, I need you to pay attention. And I want to show you how we can actually derive that. If this is a multivariate density, okay, please pay attention. This is a multivariate density. Now, I want to plug in wherever I see that, I plug in that. This is a notation for precision matrix. This guy, that's a notation. The guy that look like a theta is a notation for precision matrix. Okay? Now, wherever I see the guy in the multivariate normal density structure, I'm actually going to replace that. When I replace that, please pay attention. I'm actually going to have this. Is there anyone who doesn't understand how I go from that to that? Is there anyone? I just replace, okay, the inverse of the covariance with the precision matrix. Okay, now, if that is what I have, please pay attention. Now, I should be ready if my intention is to estimate. What do I want to estimate? I want to estimate precision matrix. I want to estimate this guy. Okay, and this is the density. Okay, I want to use the method of maximum likelihood. Okay, now if I want to use the method of maximum likelihood, I'm actually going to write the likelihood for this distribution. Likelihood is just the joint PDF. Can you see that? The likelihood is the joint PDF. When I did that, I'm actually going to have this. Okay, please pay attention. After writing the likelihood for that, this is what I got. The likelihood is, you actually have a joint, the product of the density function. Okay, now you're actually going to arrive at that. Now, when I arrive at this right now, okay, the next thing that I'm actually going to do is, because this is multiplicative, likelihood function is multiplicative, and I want to perform an operation of optimization. Optimization here, my objective function is I want to maximize. Don't forget, I actually want to obtain the maximum likelihood estimate of precision parameter. That's what I want to estimate. Okay, now this is multiplicative. When it is multiplicative, I'm actually going to introduce a log, right? Logarithm. Okay, the logarithm of the likelihood. Okay, please pay attention. Taking the logarithm, I'm actually going to have this. Please pay attention. Okay, I find myself here after taking the logarithm of the likelihood. Why is it that I cannot optimize? It may be kind of difficult for me to optimize the likelihood function directly, because the likelihood function is multiplicative. Okay, don't forget, if I want to optimize, I'm actually going to use I'm going to differentiate. Okay, it may be tedious. it may be cubation to obtain a derivative of a multiplicative function, and that is the reason why we want to convert it to additive function. Additive function is very easy to differentiate, and that's why you take the logarithm. When I take the logarithm, you see what I have right now. Now, when I take the logarithm, of course, because I'm actually going to be using the principle of optimization, this guy is immaterial. That's a constant, right? That's just a constant. So that can leave, because when I differentiate with respect to the precision parameter, that guy is going to be 0. Does that make sense? Now, this is what I'm actually having now. This is what I'm having now. But you know what? I want to do further splitting. If you take a look at this guy, oh my God, I'm seeing something here. I'm seeing, if you take a look at this guy, I'm seeing something that has to do with covariance and precision matrix. I'm seeing something that has to do with covariance and precision matrix. Now, do you know that guy can actually be reading? That guy can actually be reading. If you take a look at what I have, right now. Okay, let me say this. I can rewrite that guy. Now, do you remember a sample covariance? That sample covariance now is actually part of this guy. If you remove this guy, the precision, this guy is the sample covariance, right? So which means I have the combination of a sample covariance and the precision matrix. Now, mathematically speaking, what does that translate into? I'm going to show you. Oh my God. This is what it translates into. When I have this guy, it is the same thing as the trace of sample covariance multiplied by precision matrix. Please pay attention. Like I said, this is sample covariance, right? If you take a look at this guy, okay, S transpose, okay, precision S is the same thing as the trace of that, which is actually the same as that. If I now want to rewrite my model now, I'm actually going to have this. This is my model. Please pay attention. That's my model now. That is the log likelihood. This is log likelihood of precision matrix. Okay, if I were to optimize, if I'm going to optimize right now, that is what I'm actually going to optimize. But let me tell you this. This comes with conditions, and I needed to pay attention. Do you know that when I optimize this, when I differentiate with respect to precision matrix and I set to 0 for situation where your sample size is greater than the number of features, you will automatically get this. Please pay attention. You will take the derivative. This is what you're going to get. And when you set this to 0, you know what it's going to be telling you? It's going to be saying that, the inverse of your precision, when you get your precision matrix and you take the inverse, it will be sample covariance matrix. But somebody is going to argue this with me. If I actually, instead of me to go through the method of maximum likelihood, why not just obtain sample covariance from the data and find the inverse? Please pay attention. You all know how to get a sample covariance using R. If you have your data set and you get your sample covariance, the moment you get your sample covariance, okay, when you find the inverse of the sample covariance, it should give you that, right? It should give you that. But let me tell you this. You can only use your sample covariance if your sample covariance is stable or is estimable. We got situation where your sample covariance is unstable. We got situation where your sample covariance is is singular. I'm going to say that again. When the determinant of a matrix is 0, can you get the variant? Can you get the inverse? If the determinant of a matrix is 0, can you get the inverse? No. But do you know that when variables are perfectly, if they near perfect correlation, okay, in a situation where there's a perfect correlation among variables, okay, the determinant of your sample covariance will be 0. When the determinant of your sample covariance is 0, what happens? You cannot find the inverse. If you cannot find the inverse of sample covariance, then it means you can't find precision matrix. Does that make sense? Now, where do you think that can happen? That can happen in high-dimensional data. In high-dimensional data, where numbers of picture is much more greater than the number of sample size. When your number of features is much more than the number of sample size, okay, you're actually going to experience a problem where your sample covariance will be unstable. It's either it is unstable, okay? The worst scenario is that your sample covariance, the determinant of your sample covariance is 0. When your sample covariance is singular, you cannot find the inverse. When you cannot find, don't forget the inverse of a covariance should be precision matrix. If you cannot find the inverse of a covariance, then it means you cannot find a precision matrix. And don't forget, precision matrix is an effort to make sure that our network is not noisy. It's an effort to make sure that we want to remove indirect effects. When you remove indirect effects, you're actually going to have a sparse network that is more interpretable. Does that make sense? Okay, now this approach, okay, if I'm only going to go this way, and the way I'm going, okay, because it's actually going to give me something that is, when I equate that guy to 0, it's actually going to tell me, sample covariance is the inverse of a precision matrix, or precision matrix is the inverse of a sample covariance. This is only possible if you are not dealing with the high-dimensional data. But if you are dealing with the high-dimensional data, please pay attention. If you are dealing with the high-dimensional data, you know what I'm going to do? I need to introduce a penalty. And that's why I need lasso. We don't just do what we do. Statistical machine learning is like a story. You can see when this problem exists, then we need this guy. Then I now need lasso to come in if that situation occurs. Now, please pay attention. Now, like I said, if there's no problem, precision matrix we're looking for is the inverse of covariance matrix. Okay, this does not apply to high-dimensional data. This is a situation where the number of sample size is more than the number of features. Okay, and in that situation, you're actually going to have a precision matrix, and in the precision matrix of diagonal, you're going to see some zeros. Zeros will indicate that you have removed indirect relationship, because that 0 indicates, of course, when you have a 0, it means two variables are conditionally independent, given that we have observed the rest. Okay, this is what I mentioned. But in high dimension, your covariance matrix may be singular or unstable. I said that the other time. When it is singular, it means the determinant of the covariance matrix is 0. You remember what we did before. The determinant of covariance matrix is what we call generalized variance. Do you remember earlier in the semester, we talked about the generalized variance, which is the determinant. Okay, now, in a situation in high-dimensional data, where the number of features is much more than the number of observation, we expect the sample covariance to be unstable. When it is unstable, that's not good. It's going to be noisy. Okay? Or the worst scenario is singular. That's the worst scenario. A singular mean the determinant of sample covariance becomes 0, and if determinant of sample covariance becomes 0, you cannot find the inverse. Then what can we do? Please pay attention. Oh my God. Oh, what we can do is to introduce that guy. That is a lasso. That is why it is called Graphical-LASSO. The reason why you bring in lasso in is the job of lasso in the conventional regression is to shrink the coefficient of any of variables with indirect effect is going to shrink that coefficient to 0. But in the covariance matrix, the coefficient is not 0, and that make the model noisy, that make it dense, that make it difficult to interpret. But with the incorporation of lasso penalty, it's going to do a job of shrinking, that indirect relationship to 0. Okay, now I'm going to tell you this. This guy here performed the job of shrinking, of removing indirect relationship that I talk about. Okay, please pay attention. Okay, now I actually you're gonna ask me what is the functions, okay, of the other one, and I need you to pay attention. Okay, now if I want to talk about this guy, that will capture how the model fits the data. Please pay attention. Trace of the product of the sample covariance and the precision measures how the model fits the data. Okay? How the model fits data. Let me tell you this. We want our model to fit the data. Okay? We want our model to fit the data, but we want a simpler structure. We don't want a complicated structure, because when the model fits the data, okay, we don't want our model to be too complicated. Okay, now, and that is why, in order for your model not to be too complicated, the lasso penalty is coming in to shrink, to remove any spurious relationship. I just wanted to get that. Now, why do I need this guy? Please pay attention. Why do I need this guy? Okay, I need that guy for stability. I need that guy for stability. I need this guy for stability. I need this guy for data fit. Just pay attention. I need this guy for data fit. I need this guy for sparsity. The 3 components are doing a different job. Sparsity plus robustness. Sparsity plus robustness. Sparsity plus robustness. Please pay attention. This is the log. This log likely function was actually derived from the multivariate normal distribution I showed you the other time. Now we got 3 terms in this architecture. The log, that det means determinant, okay, and that is for stability, okay. But somebody is going to ask me, how is the stability guaranteed? Then I'm expecting this guy to be positive definite. Please pay attention. You know what I mean by positive definite, because it is the positive definite that will guarantee stability. Now, when I say positive definite, okay, if the quadratic form involving that guy, involving precision matrix, the quadratic form must be greater than 0, which means I only want positive eigenvalues. What did I say I want? I want positive eigenvalues. Okay? With positive eigenvalues, Okay, the log of the determinants of the precision matrix is actually going to attain the stability that I actually mentioned. Now let me tell you this. It's going to make the whole team behave well numerically, because we're actually going to use iterative means of seeking redress, and we need some stability. Okay. Now, is there any question here? Is there any question? Is there any question? Like I said, the matrix need to be, if it's only when the matrix is well behaved that it can be well interpretable. Please pay attention to that. Now, you can see the job of all of that. Okay. Now, let me also tell you this. The objective function here is maximization, and the effort put in place here, we make sure we are working with a concave function. If I want to, because I want to, with concave function, I will be able to translate local maximum into global maximum. Don't forget, I want to perform, I'm looking for maximum likelihood estimate. You remember earlier in the semester when we were minimizing, we were focusing on converse function. Okay, with converse function, local minimum translate into global minimum, but here we need a concave, and with this in place, it's going to make sure we have a well-balanced structure, that will give a unique solution. Okay, I think I've mentioned that. We want that ensure stability, feed the data, induces sparsity. Okay, and I talk about positive definiteness. Okay, the positive definiteness is when that happens when the quadratic function, because this guy is a quadratic function. Okay, that guy is a quadratic function. The quadratic function has to be greater than 0 before you can talk about positive definiteness. We don't want a negative definiteness. Okay. Now, in that situation, like I said, all eigenvalues have to be positive. The determinant of that guy will be greater than 0. Of course, it is only when the determinant of that guy is greater than 0 that we're going to talk about the inverse. Then in that situation, that would justify the Gaussian model we're using. Does that make sense? That would justify the Gaussian model that we are using. Okay? Why positive definiteness matters, okay? Because of that very log of data theta. Okay? So take a look at that. I think I've given, okay? Now, I said this guarantee Gaussian precision matrix, numerical stability, and meaningful graph interpretation. Okay, I think at this junction, let me see. I'm actually going to go into, but let me warn us. Let me warn us here. Okay, what if in a situation where you have a small eigenvalues or negative eigenvalues? With negative eigenvalues, your model is invalid. Please pay attention to that. And if your model is invalid, the log determinant term will collapse. Of course, can I even have a log of negative? Mathematically, can somebody press your calculator? Log of negative, does it really exist? Okay, now moving. I think I'm going to go back because I'm going to be going back and front. Okay, I'm going to stop this one now. I'm going to go back to the material. Okay, get to material that we're actually using. Okay, and I've uploaded these two material. We're going to work on these two material this week. Okay. Okay, please pay attention. Okay, pay attention now. I think I've walked you through all of that. If you don't understand, ask me a question. Exam is around the corner, right? Okay. Now, I just wanted to take a look at the network. Take a look at this guy. If you look at this guy, okay, you actually, do we have between S1 and S4, is there an arrow? Please check. Is there an arrow between X1 and S4? Imagine if I put an arrow. Imagine if I put an arrow between this and this. Okay, let me do this. Let me use this one. Imagine if I put an arrow, if I also put an arrow here, the model will be complicated. Okay. Now you know what what this guy mean here. We're trying to say two variables are independent, given that I've observed the rest. Look at this. You know what that guy is trying to say? I don't have arrow between S1 and S4 because I've already observed S2 up to X8, which means between X1 and X4, we only have indirect effects, indirect relationship. And precision, using the graphical lasso, using the lasso will shrink the coefficient that relate X1 to X4 to 0. Because while we're removing that relationship is actually noisy. Okay? So that's why we're removing that. Just pay attention. Okay? Now, and this is the definition. When two variables are conditionally independent, we expect their corresponding precision matrix to be 0. Please pay attention. Okay? Situation where precision matrix is not equal to 0, then it means the relationship they have is a direct one. You cannot eliminate direct relationship, but we can eliminate indirect. Does that make sense? That's what we mean. Look at that. When the conditional independence hold, that can lead to sparsity. Sparsity can lead to conditional independence. And do you know that with this, that will make our complicated graphical structure simple. Does that make sense? Okay, I'm moving. Now, oh my God, this is a precision matrix. Now, you can see we got 0 zeros in some, right? Okay, where you have 0, 0, 0, if you draw the network, there's not going to be an edge. Now, let me tell you something, which means if I want to draw a network, I can use the idea of precision matrix to draw my network. You remember the other time that I said, if you want to draw your network, you're going to use the idea of E-climbing, okay? Or you use an expert knowledge, a domain expert knowledge. If you don't want to go through all of that, with precision matrix, you'll be able to draw a very simpler network because the precision matrix will eliminate any indirect relationship that may be spurious, that may make the the graphical structure to be dense. Okay. Okay, now, I show you this other time. This is a situation where everything is good. You can only optimize this log of likelihood function if your number of observation is greater than the number of features. You cannot use this in high dimension. The one you're going to use in high dimension, you're going to incorporate what? Lasso, plenary. Okay? Which is what I'm explaining here. Take a look at this guy now. Now I said, for classical theory, do you know why the number of observations need to be more than the numbers of features? Because maximum likelihood approach actually require a large sample size. because the result from the maximum likelihood used to be biased, but it is asymptotically unbiased. You know what we mean by asymptotically unbiased? When the sample size is large enough, the bias will converges to zero. Okay, which is what we're saying here. Okay, when sample size MLE converges to the truth, when the sample size tends to infinity. But what of in a oh my God, what of in a situation, this in a high dimensional data where the number of sample size is less than the numbers of features, then your covariance matrix is actually going to be a rank deficient. When you're not going to have a full rank. If you don't have a full rank, there's possibility the determinant of the covariance matrix will be singular. When it is singular, you may not be able to get the precision matrix, and because of that, I'm actually going to say even I say MLE does not even exist in that situation. And that's why we need to incorporate lasso. And that's why this guy is coming in. The lasso penalty is actually coming in. I told you the other time, the lasso penalty is actually to enforce sparsity, to remove any indirect relationship that may make the model to be noisy. Now, when you do that, oh my God, if you take a look at that now, when you do that, okay, then we actually going to have what we have here. Now, this is where I'm actually going to start. Okay, I'm going to start from here on Wednesday. Okay, this approach is very, very recent. It was actually discovered by Friedman, Hastings, and Sibishrani in 2008. Very, very recent. Okay, I'm actually going to show you how they use a block coordinate descent, to be able to achieve that, because you are, incorporating a lasso penalty into a log likelihood function require, some kind of advanced knowledge, some additional information on how to moving forward. Okay, I'm actually going to explain that to you. Okay, before I go today, I've introduced the Gaussian graphical lasso model and the idea behind that. Our covariance cannot answer a question that has to do with direct relationship. Our covariance will mix both indirect and direct. And because of that, the structure is going to be noisy. Interpretation become an issue. That's why we need lasso. We want lasso to come in to shrink, the coefficient associated with any two variables that are having a direct relationship to zero. Okay, that's why lasso is coming in. And of course, we started using multivariate normal density, but you know what I'm doing in my present work? In my present research work, I'm reparameterizing multivariate normal for this. What of in a situation where the underlying distributions of the features are normal and they do not follow multivariate normal? Okay, Friedman, Hastings, and Chief Shirani did not undo that, but I'm going to address that in my recent work. That's what I got for you today. Make sure you all stay safe and have a lovely day. Bye for now, everyone.